So just a little bit recap. ETS models, they give us short-term forecasts. They give us decomposition of a time series into trend and seasonal effects. They are mainly used for monthly, quarterly, yearly, not high frequency time series. This is abbreviation acronym for error, trend, seasonality. And if you'd like to have a book, the book is Forecasting Principles and Practice. They are also called exponential smoothing models. So they have a long history, but they have a long history. I think they started like 70 years ago. And they have started like simple forecast algorithms without, they origin, I think it's something like, maybe I'm missing, but roughly 1960s, so roughly that years. And in that time, they were considered like just forecasting formulas without statistical model. So they gave in that time they were used for point forecasts, but without underlying statistical model. It was not possible to produce interval forecasts, to speak about predictive intervals, to speak about confidence intervals, hypothesis testing, model comparison, and so on. So they will use just this is forecasting formula, yeah, something like let's say that my future forecast is alpha times past value plus 1 minus alpha times past forecast. So something like this. So next forecast is some weighted mean like that. So there are many more other exponential smoothing models, but this is the most primitive one. So future forecast is like weighted average of past value and past forecast. Okay, but in I think something like 15 years ago, so in 21st century, there was a change. They have a statistical statistical model behind these formulas, forecasting formulas was discovered. So now these models, ETS models, are full statistical models with underlying assumptions. And so we may compare models, test hypotheses, build the predictive intervals, and so on. So starting like 15 years ago, there was a good theoretical advance in studying of these models. So sometimes in a book, you may encounter all the presentation of these models without statistical assumptions, just like this is forecasting formula for exponential smoothing model. And we will use it, and it works more or less well in some circumstances. And starting from, I think, 2010, we have statistical assumptions. This U has normal distribution. So we have such and such coefficient to estimate. We use maximum likelihood. So we have a standard approach. And forecasting formulas are the same. But we can not only have point forecast, but we have also interval forecasts. Okay? So there is a short story behind these models. And so they have, in old days, this is like they were called exponential smoothing models, and modern history is they are called ETS models. But basically, they're the same forecasting formulas, but with or without statistical assumptions. That point is clear. Can we continue?
Yep.
Yes.
Okay. So let's introduce. So let's consider first idea without error, without noise. So first, to understand the idea, let's imagine that we have no noise. So no random noise. So a very simple model. A very simple model says that level, L will stand for level, B will stand, this will be the will be a level of an indicator. I don't care which one. BT will be growth rate, and ST will be seasonal component. And without noise, everything is simple. So we just have something that grows up, something that just grows up, and sometimes we add, let's say, +2. Sometimes we subtract 1. Sometimes we subtract. Sometimes, and once again, plus, minus, minus, plus, and we have a repeated a sequence of seasonal effects. Just the trend goes on. So for this case, when we have no error, we will have equations like that. So YT will be observed value. L level without seasonal effects. So that will be my LT, will be T. I think in blue, this will be my
I'm sorry, may I ask a question?
Yeah.
Since we know the level, I think this is like the trend. Why do we need BT?
BT is a rate. In our case, it will be constant. It will be the slope.
Yeah, that is what I mean, because BT can be found like LT minus 1 divided by
exactly.
LT minus 1.
Exactly.
No?
Because we will introduce noise in 5 minutes.
Okay.
In this setup, when there is no noise, you are completely right. So in the case when there are no noise, you are completely right. LT is just previous level plus previous growth rate. BT is just BT minus 1. It's constant.
Yes.
And YT is just when we have no noise, everything is simple. YT is just LT minus 1 plus BT minus 1 plus, let's say we have a quarterly data. So we have like 4 seasons: first quarter, second quarter, fourth quarter, third quarter. Okay, so we have S T minus yeah, like we will add like S T here, yeah, or maybe ST minus 3. Okay, and ST is just ST minus 3. Oh, sorry, 4. We have 4 season. Okay.
Yes.
And could you please explain seasonal factor in this equation?
Just these arrows, like
Maybe on some data sample, just some associative.
Oh, what's your question? Once again.
This seasonal factor in the equation where we have ST minus 4, what is it?
Yeah. What is it? Because we have, so that means, because for the moment we are studying no noise case, just to understand the idea, we will introduce noise in 5 minutes. Then we basically say that the effect in current January, sorry, not current January, first quarter year, is the effect of first quarter of previous year.
Which means that it is the same and there is no effect. No?
No, it doesn't mean the same. So look at the picture. So let's say this is so this is first year, 1, 2, 3, 4. This is second year, 5, 6, 7, 8. This is year number 3. T is 9, 10, 11, 12, and this let me add in green. Yeah, this arrow is S5. This is seasonal add-on, and S5 is exactly equal to S9, but it's different from, and this is seasonal add-on to S6. It's not equal to S6, that is equal to S10. Okay?
Yes, yes.
So, so they are not all the same. The effect of, so imagine we speak about months. So the January effect is constant. Every January we have, let's say, 10 more million rubles consumption. Okay? But this additional seasonal effect is not like in February. January 2020 is like January 2021, but it's not like February 2020. Okay, so that doesn't mean it is constant. It's repeating, but it's not constant. Okay.
I see.
Yeah.
Yeah, like cyclical.
Yeah. It's some authors distinguish between cyclical and periodical effects. So you need to be careful with this term. Some authors do not care about this difference, and some also, it depends on the book, the terminology. But sometimes cyclical means different things from periodical. Some authors just use these two terms with the same meaning, but some authors say that cyclical is something when the length of period can change, and the periodic is when the frequency is constant. So, for example, if you have like every 12 months, every year has 12 months, and every January is like January before. So some authors say it's periodic seasonality, and or just seasonal effects. And sometimes when, for example, you speak about sun activity, or I don't know, population of tigers, and it has some cycles, but these cycles have not constant length. So, for example, sun activity is roughly 11 years, but sometimes it's more than 11 years, sometimes it's less than 11 years, and so cyclical is a word reserved to such behavior when the frequency, when the length of a period can change. But some authors do not distinguish, and they say cyclical and periodical and seasonal effects. But be careful. In some books, there is a subtle difference between cyclical and periodic behavior. Okay.
Okay, thank you.
So that's a model without error. Okay. And now, even now we have some. So this model has no error term, but there are some parameters to estimate. Let's look how many parameters do we need to estimate for this. This is bad model. It has no random effects inside, but already we have a good question. How many parameters do we have? How many parameters do we have? So that's not easy question. That's a tricky question. So that's a tricky question. So to completely determine the line YT, how many parameters do you need? How many initial conditions do you need?
B0 and 2 parameters.
You need B0 to start to specify completely the model. You need initial conditions. Yeah, when you have a difference equation or differential equation, you know that you need initial conditions. How many initial conditions do we have here to completely specify the model? You need B0. Okay, if I say that B0 is 2, how many more initial conditions do you need?
L0.
L0, if I say L0 is, let's say, 100, is it enough to completely calculate the future values?
No, we need each of the seasonal effects.
Yeah.
What else do you need?
Each of the seasonal effects.
So how many? So my question
4
remains,
of them.
how many parameters do we have?
4.
4 of them. 4.
Almost 4. You are almost right. That's a tricky question. If I specify them like, so there is a subtle trick there. If I specify, for example, S0 is 2, S minus 1 is 3, S minus 2 is 4, S minus 3 is 7, that will give me a very strange dynamic. Do you see why the dynamic will be very strange? Because your level will be there. This is LT. They started at L0. It goes up by 2 every time. So you will have something like LT. And because your seasonal effects are always positive, that will be the level. And your actual observed YT will be 2 times higher, 2 units higher, 3 units higher, 4 units higher, 7 units higher. Then 2 units higher, 3 units higher, 4 units higher, 7 units higher. And YT will go like that. So this will be YT, and this will be LT. And it's something strange in this example that YT is going like this. So YT is always above trend. That's YT is always, this is your YT, and this is your LT, and that's something strange. I wouldn't call it trend if YT is always greater than trend. Yeah.
See what you mean.
Trick, which one? How would you change that strange behavior that YT is always greater than LT?
We need to subtract one of the seasonal effects and take it
Yeah. Seasonal effects sometimes should be positive and sometimes negative. Okay, so this we don't specify because we just say that S0 plus is we not need it, because S0 plus S minus 1 plus S minus 2 plus S minus 3 to have interpretable seasonal effect. This is higher than trend, this is lower than trend, and we move up. Because if we are always higher than trend, then trend is not a trend. Okay, you see my point?
So it should be 0, right?
Yeah, that should be 0. So in this case, we have 6 parameters in total. We have additional equation to make our model interpretable. We have additional equation S0 plus S minus 1 plus S minus 2 plus S minus 3 equals to 0. to make, because otherwise it would be strange that you have a trend that is below, always below, not just once or twice, but it's always below your actual y. That would be strange. Okay, bt is constant. In my example is bt minus 1. So in this case we have 1, 2, 3, 4, 5 parameters to estimate. Okay, everything is clear in the model without error, or any questions about the model without random noise? Because now I will introduce random noise in these equations. Okay.
Yes, everything's clear, but it's one particular question. You mean
Yeah.
we need to estimate 5 parameters in this particular model with seasonal data?
Sorry?
You mean that we need to estimate 5 parameters in this particular model, which includes seasonal data, but not like monthly?
Yeah, we need to estimate 5 parameters. So we can use nonlinear least squares. So this model can be estimated. So, so you may, for example, minimize by using L0, B0, S0, S minus 1, S minus 2. You can minimize something like actual y1 minus prediction of y1 made at 0 squared plus y2 minus forecast, one step ahead forecast plus yeah, you may estimate this model. This model can be estimated by using nonlinear least squares. That's not a problem. And n minus 1. Yeah, you may estimate this model by estimating five parameters. Forecasts are very simple in this model. You cannot have interval forecasts because we have not introduced random noise variance, and so we are not able to do interval forecasts. But if you'd like to stay, who can guess the forecasting formula? Y t plus 5, given you start at t, is given by, who can forecast yt plus 5?
Do you mean it is L4 plus B4?
It's LT plus, we do 5 step ahead. So we add 5 by BT. So that plus L plus
S minus 3
plus S T minus we work with quarterly data.
Wait, shouldn't it be minus S0 minus S1 minus S2?
Sorry, I don't get your question. So let me finish the formula and let's discuss your question. Okay, so this is forecasting formula. Maybe it's better to start with one step ahead forecast. If we live in T and we have all past values, then we need to take level plus growth rate plus corresponding seasonal effect. But the seasonal effect of T plus 1 is just the seasonal effect of T minus 3. And the seasonal effect of T minus 3, let's imagine that we have already estimated it. Any questions?
No.
No.
Excuse me. May I ask a question?
Yeah.
Could you once again explain Why do we omit the fourth seasonal component?
Where?
In the previous slide, yeah.
Here?
Yeah.
Because I have one more equation. To have an interpretable model, I have one equation, and you just cannot say that seasonal effects are always positive. That would be a crazy idea. Why you cannot have all seasonal effects positive? You have a trend. This is your trend. You'd like to introduce this trend. And if all seasonal effects are positive, then your actual y will be always above your trend. And this is crazy interpretation. This is my actual, I don't know, GDP, construction, consumption. I don't care about the meaning of an indicator. So this is my actual YT, and this is trend component. So this is trend component. That's something strange. Yeah, don't you find it?
Yeah, agree.
So to have something interpretable, you would like to your indicator changes, and this is YT and this is LT. So you need to have sometimes seasonal effect should be positive, sometimes seasonal effect should be negative. So to have interpretable model, we have a hidden equation that initial sum of seasonal effects is 0. We have 4 seasons in our case. We speak about quarter. So if you have monthly data, so you have the sum of 12 monthly effects is 0. Okay.
Yeah, now it's clear.
Okay. Now if everything is clear with the model without noise, then let's just introduce noise, and we will have ETS model. So finally, model with noise. Model with noise. We don't use model without noise. I have just started with model without noise to make it to simplify introduction. We never use model without noise. So that's just to introduce the idea of decomposition of my YT into LT, BT, and ST. Okay, so that just was the idea, but we never use model without noise. Okay, so I will just copy previous equations. So equations are one equation that to have interpretable seasonal. So one. So first, maybe the most simple is BT. So that is a simple equation, BT. Okay, so that will be ST as ST minus 4 with normalizing equation like that. We have LT that it is so no seasonal effects. So that's called a level. It's previous level plus previous growth rate, and with seasonal YT is just LT minus 1 plus BT minus 1 plus ST minus 4 in our case. So we add noise. We say YT has normal distribution with mean 0, variance sigma squared, and they are independent. Okay, and I will introduce my noise into previous equations. Okay, so I add noise, and so let me write in red. Maybe it would be better to see the difference. YT has normal distribution with mean 0, variance sigma squared u, and they are independent. and I will introduce. And the idea of ETS model is that noise may have a different impact on current value and long-term trend. So, for example, if something happens, some good news arrive. These good news may change actual observed Y, and they may change the growth rate. Okay, if some good news arrive, they may change actual Y, and they may change current B. Okay, and they may change current ST. Yeah, but so noise can influence everything. So, for example, if today machine with many dollars in cash will crash here in the street, and the street will be covered in dollars. I think there will be more people in the street today because they probably would like to grab some dollars. Maybe this event will attach attention tomorrow. So this event will have immediate effect, and maybe this event will influence the popularity of this street in a long run. Maybe there will be even a small monument to this accident. So the idea that this noise may influence all my equations except normalizing one. So yt may influence this equation, yt may influence second equation, ut may influence third equation, and ut may influence all equations with in exception of normalizing equation. Okay, so the idea that ut may influence all equations, but with different intensity. Usually the effect on current value is the biggest one, and long-term influence or seasonal influence is less than immediate influence. Okay, so I will introduce ut in all the equations, but with different weights. The idea is clear?
I'm sorry, may I ask a question?
Sorry?
May I ask a question?
That's a stupid question, whether you may ask a question or not. Just don't waste my time. Just ask the question. May I ask a question? May I ask a question about whether I may ask a question? Just ask a question.
So since the expected value of ut is 0,
yeah,
isn't it reasonable to assume that in the long run, the effect of these shifts will be cleared?
No, no. If, for example, you have so why it's no, why it may have a lasting effect. So you have ut has influenced bt, and future expected u next you don't know why they should cancel out. No. Okay, so let me just add the u in different equations. So I add here ut, I add here ut, but with another weight. Let's call it alpha. I add ut there with another weight beta, and I add ut there with a weight gamma.
Sorry.
Okay.
Please switch.
Yeah.
Could you once again state, you said that the current value is influenced the most, and the long-term effect?
Yeah. So alpha, beta, and gamma will be less than will be less than 1.
Yeah, but the current value is influenced the most, and what then? What I mean, what components will be influenced less, and what components will be influenced more?
So I don't know whether beta is greater than gamma, but the idea is beta is less than 1, gamma is less than 1, alpha is less than 1.
Oh, okay, I got it. Thank you.
Okay, and this model is ETS, where everything is additive. So that is the full set of equations for ETS AAA model. What does it mean, A? We have additive. A stands for additive error. So it's E, additive error. T, additive trend, and S, additive seasonality. Seasonality. We may have multiplicative models, so that's not only one possible model. So before moving a little bit to multiplicative models, let's check how many parameters do we need to estimate by maximum likelihood. So how many parameters? How many parameters to estimate? How many parameters to estimate?
Five parameters.
No. Without noise, we have 5 parameters. And now we have
8.
how many?
8. No?
10 if
Alpha,
we
beta, and gamma.
So without noise, how many parameters we have to estimate?
5.
5. Okay. Just count how many new parameters are there. Just take your fingers and just count how many new parameters do you see in this system.
1.
3. Alpha, beta, and gamma. No?
Who can see more?
Sigma squared U,
Yeah. So
Oh, yeah,
how
yeah.
many parameters in total?
9.
Yeah, you have 9 parameters. Okay, 9 parameters. So that's 5 plus, do you see new parameters in this system? They are sigma squared, alpha, beta, and gamma. So we have 9 parameters in total. Okay? Is that clear? Just count them. Just
Yeah, sure.
that's like this. You may put like there, like here, and like here. Okay, and 5 all parameters from the system without noise. We never estimate system without noise. It's too simple and the forecasts are too bad. But with and these models, when we estimate it by maximum likelihood, because we can write the density of y1, the density of y2, the density of y3, and so on. Yeah. Okay. Let's before moving to, let's solve a simple exercise to understand how computer makes interval forecasts. Let's use the system. So let's imagine that you have so what is the logic behind? So the procedure. So the procedure is like this. When you have real data, you observe y1, y2, y3, yt. Yeah, you do not observe L, S, B. They are artificial. They are just they are a meaning to interpret a model, to decompose Y into trend, seasonal effect, and so on. So you observe only YT. These are observed values. And UT, ST, BT, LT, these all are unobserved. This is just a set of like it's our view of how YT is constructed, but they are not observed. And using maximum likelihood, we estimate L0 hat, B0 hat, S0, S minus 1, S minus 2 hat. These are old parameters without noise parameters. And we also estimate simultaneously 4 new parameters, alpha, beta, gamma, and sigma squared U. So we using these using maximum likelihood and real data about Y1, Y2, Y3, YT. So we have no data about UT, ST, BT, LT. So first step, computer estimates 9 parameters for this model using maximum likelihood. Then using formulas, using model formulas, you can actually decompose YT into, so you can calculate L1, L2, L3, LT, B1, B2, BT, L1, L2, LT, S1, S2, ST, U1, U2, UT. So we just use these formulas. So if you have B0, so you can calculate B1. If you have L0, you can calculate L1. Okay. And next, you can, the third step, you can forecast. You can forecast. Let's just omit the first step, but let's see how we can calculate all the stuff we have, and let's see how we can make forecasts. Okay. Yeah. So let's reproduce. So we will not estimate. So we will estimate using computers using maximum likelihood. Let me just reproduce by hand to better understand how it works. We will reproduce by hand step 2, and we will reproduce by hand step 3, and basically next time we will estimate ETS models, okay, with computer. So, but to better understand how it works, let's imagine just to understand better step 2. So you can, so once again, to have all the equations before you, I will post I will just post here. Okay, so all equations are there. So all ETS equations are there. Now, let's imagine that we have some estimates. So imagine that L0 is 100, B0 is, I don't remember, 2, S0 is 1, S minus 1 is 2, S minus 2 is 2, alpha is 1 over 2, beta is 1 over 2, S gamma is 1 over 2, and sigma squared is 4. And imagine you have Y1 that is 101, y2 is 105, and just let's understand maybe I will just even select part of this formula. Oops. Oh, I will even make a cut in the Telegram chat to simplify, because it's a little bit, it takes a little bit of time to copy all equations. So that will be t equal to 0, t equal to 1, t equal to 2. I will not fill everything, but roughly I have yt, that is no yt for 0, 101, 105. I can fill in ut, lt, st, bt. So let's work. So starting values, we don't need this. LTEL starting is 100, S 0 is 1, B0 is 2. Who can calculate
Y0 forecasted.
Y1? Who can calculate Y1?
Is it Y or U?
Sorry, U1. Yeah. So you have equations. You have equation for Y1 is just L0 plus B0 plus S 1 minus 4 minus 3, yeah, plus U1. L1 is just L0 plus B0 plus, we have no seasonal effect here, plus alpha times U1. And
Isn't it plus 5?
sorry, what is plus 5? Where is plus 5?
Oh no, U1, it's plus 4. It's 4.
Why it's 4? So that's my question, how to calculate U1?
Because we need to sum up L0, B0, which is 102. And then the seasonal factor is minus 5. So
Yeah, we have that we know. So we have 101 is L0, L0 is 100 plus B0 is 2 plus S minus 3 is minus 5 plus U1. And so we recover U1 from the first equation. Yeah, so we have recovered U1. U1 in our case is, I think it's 4, yeah?
Yeah.
yes, it's 4.
Yeah, it's 4. So we know U1 it's 4. Now we use this equation. So the first, so let's, this is the first indicator we fill in our table. Now let's move on to L1. How we can find L1?
How did you calculate S with sub-index -3?
We know that we have equation that is S0 plus S1 plus S minus 2 plus S minus 3 is?
Okay, got it, thank you.
Is 0. So maybe it's second. Yeah, you're right. It's second in calculated. The first we have, the first thing we calculate is the missing S. So F. Yeah, you are right. It's the first thing we need to calculate. It's -5. Yeah, you're right. We need first we calculate the missing S. then we calculate U1, then we proceed with L1. How to calculate L1?
104.
Yeah, we use equation. L0 is 100, B0 is 2, alpha is 1/2, U1 we already know it. It's 4. So we have, I think, 104, yeah?
Yes.
It's the third object calculated. Now we can calculate S1 and B1. Who can
S1
calculate?
is -5.
S1 is, let's be careful. S1 is S minus 4 plus gamma times U1. Yeah, do not forget that we have noise in our model. We don't just blindly copy past seasonal effect. Seasonal effect can change. For example, the winter now are warmer than before, so less people buy, I don't know.
Wait, it's S-3.
Yeah, S-3. Yeah. 1 minus 4. So I should write 1 minus 4 there. So it will be S-3 plus 1/2 times U1. And it will be -5 plus -5 plus 2. Yeah,
Yes.
it's -3. So we have -3. Who can calculate B1? What is the equation for B1? I have copied in the Telegram chat, or you may have BT is just BT -1 plus the effect of noise
Gamma.
plus beta times UT. So in our model without noise, we have constant trend. In our new model, the growth rate, the slope may change. So we may have, so now the slope is high, and then the slope will be lower and so on. So what is B1?
4.
It's previous B, it's 2 plus 1/2 times U1 is 4 is 4. Okay? And then we just continue. So we calculate as in previous case, we just will calculate indicator 6, 7, 8, 9, and we can feel if we have data about Y1, Y2, Y3, and Y is observed. Y is observed. We have data about Y. Then we can, line by line, we can calculate this table. Okay? Do you see how we can calculate it further?
Yes, but I have a question regarding seasonal effects. So the equation that we wrote, S0 plus S-1 plus S-2 plus S-3 equals 0, does it regard only these 4?
No. Only so this equation is exactly satisfied in the beginning, and it's roughly satisfied later. So not always the sum of 4 seasonal. So for example, they roughly the idea they should be the sum is almost 0, but noise can a little bit push up or push down the sum of seasonal effects. It's roughly 0 always, but seasonal effect this error can influence these.
Okay, that is all that I.
Roughly, so it's exactly satisfied in the beginning, and it's roughly satisfied later. So, but even the fourth seasonal effect, the S1 will not be equal to exactly -5. It's a little bit less in our case Okay, the step 2, when we have 9 parameters, how we can decompose the trend into my YT into components is clear, yeah?
Yes, clear.
So this, what is the step? So what is the meaning of this step? Given 9 parameters estimated by maximum likelihood, we can decompose the whole time series y1, yt. We have decomposed it into components. So we can say this is a trend, these are seasonal effects, this is a growth rate. The growth rate is changing, so we can extract these from our algorithm, okay? And now, so we just use these equations, and basically the extraction process is simple. We will, obviously, we will do it using computer, but just to understand how computer does this. Okay, step 3. Step 1, we omitted. Our course is not so theoretical, so I will try to explain what computer does, but I will not dwell into some details. What is exactly the formula for maximum likelihood? But basically, as all variables are normal, then that's just a multivariate normal distribution, and you maximize maximum likelihood, that is just a multivariate normal distribution. So you have a multivariate normal joint density, and that depends on 9 parameters, and that's estimated. But the problem is that with ordinary least squares, you have explicit formulas. I have explicit formulas. Beta hat equals 2. Bam, 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 bam. And in ETS models, there are no explicit formula for parameters. So you have a function, maximum likelihood function that can be maximized, but there are no explicit formula. So the function is very complex, and no explicit formula. So that's happy news for students, because no one can ask you to derive 9 estimates of ETS model by hand, because it's not possible. Okay, so step 3. Let's imagine that we have let's imagine that we have all the parameters. I will just copy them as 100. Okay. Stop. Step 3. You have calculated all. So you have sigma squared, that is 4. You have let's say beta 100. Let's say the last observation we have is t equal to 100. We have 100 observations. So we have calculated last b. Last b is let's say 3. We have calculated last l. Last l we have field rows of table. Last l is 2205. Let's say that alpha is 1/2, beta is 1/2, gamma is 1/2. What do we need more? We have S seasonal effect 100 is plus 3. Seasonal effect 99 is plus 2. Seasonal effect of 98 is minus 4. And seasonal effect 97 is roughly, they will sum up to 0. But because of noise, they not always sum to 0. This sum may not be exactly 0. It will be around 0, but not exactly. So in my case, I will say that my sum is minus 1. That's okay. When we have introduced noise, that's fine. In a model without noise, that's not good. Okay, and my question is, construct 95 predictive interval for y101. How can we construct predictive 95 predictive interval for y101 for the next value? So we have basically 3 stages. First, we estimate parameters, then we decompose observed y1, yt into components, and then we can make predictions. So what is 95 predictive intervals for the next value? How can we do it? Just write the formula. What is the formula for y101? What is the formula for the next y?
L100 plus B100.
It's L100 plus
B100.
B100. So it's past level, past slope, plus
Plus S97
past seasonal effect,
plus
plus
U.
U101. That is independent of what we know. So in my case, the next U is just 205 plus 3 minus 2 plus these. So it will be like 2006 plus 101. I don't like to flip a page. I will finish calculations there. So I see that y101, given all information, given ft, given f100, has a normal distribution with mean 206 and variance. Variance is introduced by this u, but I have variance of u. Variance of u is variance. This is variance of u. So I have variance 4, and so my predictive interval is 206 minus 1.96. That's the critical level for normal distribution, or square root of 4. So we have built a predictive interval for the next value. Okay. Any questions about predictive intervals?
We defined. Can I please ask? Well, so we defined that we can like have parameters for error. Why don't we use alpha, beta, and gamma to kind of predict the next error? Why do we just?
Yeah, they will be used, but for 2 steps. So if you, for example, calculate, yeah, they will be used. Yeah, you are right, but they will enter our game. So if you try to calculate y102, what is it? It's L101 plus B101 plus S98 plus Y plus U102. So let's put this L101 and B101. So this we know we have this. So what it will be? It will be L100 plus B100 plus alpha times U101. So this is L101 plus what is B100? It's B100 plus beta times U101 plus S98 plus U, and finally I will have 205 plus, as far as I remember, it was 3 plus 3 plus L. This was 1/2 times plus what is B plus 3 plus 1/2 plus S, that was -4, as I remember, plus U102. Yeah, am I right? Or I have missed something?
Seems like you did everything.
Yes.
So this is our alpha and beta. They play important role, but not in one step ahead forecasts, but in two steps ahead forecast and more steps ahead forecast. So in my time series model, I will have so something. It will be 3 plus 3 minus 4. It's 2. So it will be 207 plus U101 plus U102. And so my U102, given my information, will have normal distribution with mean 207. And these two terms will influence the variance. The variance will be 4 plus 4. And 95 predictive interval will be from 207 minus 1.96 times square root of 4 plus 4 up to 207 plus 1.96 square root of 4 plus 4. So we have, and the alpha and beta are important in that case, okay? Okay. So ETS model may have, for example, what we have described. We have finished the description of ETS AAA model when we have additive error, additive trend, additive seasonality. We may introduce many more examples. So we may switch off, let's say, switch off seasonality. So you may consider ETS AAN. So that means no. So you just remove, you just say ST is always 0. So for non-seasonal data, you can switch off seasonality. Or you may switch off trend. So you may have ANA model. So that means no. Yeah. T is the second letter. First is error, second is N. So that means you switched off BT. BT is 0. Okay. Instead of equation for BT, we have a simple equation for BT. And so we have considered AAA model, but there are many variants. For example, there is ETS MMM. M means multiplicative. I will not go into details because my part of the course is not theoretical. It's more about R, but I feel that I need to introduce something at least. I will not go into details, but let me just write one. All equations will be a little different with some replaced by multiplication, but in it I will just write one equation to show you the idea. All equations are available by the link. So if you like to have equations for the model, so you just click on the link or in the book Forecasting Principles and Practice. But just to show you the idea, what does it mean, multiplicative effect? In ETS AAA, YT is LT minus 1 plus BT minus 1 plus ST minus 4 plus UT, and in multiplicative model, can you guess what will change?
Instead of plus, they will be multiplied by?
Yeah, you're right. So with one subtle trick, we have UT that is once again that is normal. So UT will be normal, and it will be considered as a percentage, like percentage difference. But the idea is very simple. You can just write YT. You are completely right, except with epsilon. So it will be LT minus 1 plus BT minus 1 plus ST minus 4. Oh, sorry, plus multiplied by. And that is not UT, because UT will be normal 0. That assumption will remain. So it will be multiplied by 1 plus UT. So that is subtle trick. But yes, the idea, we can combine effects in a multiplicative form. Okay.
Okay.
So basically, that's all. My introduction into ETS model is a little bit short, just one lecture class. I don't know. So next time we will estimate these models in R. But as a final conclusion, so you have a class of ETS models. So these are ETS models. You have something like ETS AAA. You have ETS ANN. You have ETS. You can combine multiplicative and additive. So you can add the seasonality, but multiply by strength. So you can say something like AAM, or you can have ETS MAM. So that's a whole set of models, roughly 20 models. And for each model, you can estimate it using maximum likelihood. Using maximum likelihood, you can estimate initial, let's say, 9 parameters. Sometimes it's more than 9, sometimes it's less than 9. Using formulas of a model, you can fill a table row by row, and you will decompose your actual Y into components. So that model has advantage over a RIMA model, because you can decompose your data in trend, level, seasonal, effect. And then you can forecast. You can have point forecasts. You can have interval forecasts. And basically, that's all we need from ETS. Decomposition and forecasting. That's all. If you'd like to learn more about this model, not how to just type ETS, pooms, Control Enter, and we have result. So you can go into the book Forecasting Principles and Practice. But my introduction into ETS models is finished. Okay.
Okay, thank you.
So that's all for today. Next time we will start working with time series. So what we expect next time, we will just understand how to organize time series into R, how to draw plot, how to, let's say, divide time series into 2 parts, train and test time series part. And then we will estimate something like naive models and ETS models. Basically, that's all I think we will cover next time. Okay?
Okay.
May I ask a small question?
You may not ask the question. May I ask the question? It's a waste of time. Just ask your question. Just don't waste time.
So the confidence intervals that we looked for, do they regard the true value or the estimation?
Sorry. Once again.
Yes, can we come back to the confidence levels? Yes, so these are the confidence level for the estimation or for the true value of Y.
You think that this is, I have considered like true alpha, yeah, and not estimated alpha hat. Yeah, in real life, yeah, you have alpha hat here. I have just simplified. I've skipped the first step of estimation. But yes, in real, you have no real alpha, you have no real beta. You estimate, so you don't have real alpha. So I have, yes, in my exposition, these are like true values. In my exposition, these are true values, but you are right. In real life, I've missed step 1, maximum likelihood estimation. And in this step, you have alpha hat, beta hat, gamma hat, sigma squared hat, L0 hat, beta 0 hat, and so on. But I skipped the first step, so I pretend that these are true values. But you are completely right. In real life, I don't have alpha, beta, and gamma. I have alpha hat, beta hat, gamma hat, but the calculations are the same.
Okay, then. Yes.
So yes, you are right. I've missed the first step because my course is a little bit. I've shown the idea: estimation, decomposition, forecasting. So estimation, I skipped a little bit. I've just said, oh, you have a multivariate normal distribution, so you have multivariate normal density. I hope you are a master student, and then you can write multivariate normal density. But yes, but if you'd like to delve into theory, how exactly maximum likelihood function looks like in this case, so read the book. That's basically non-examinable part, because on the exam you will have a practice assignment, so you need to be able to forecast monthly data and not to write. So it's good idea to know, to delve into details and to know how to write this maximum likelihood function, but that will be not on the exam. Okay.
Okay, yeah, that's clear.
I would like to ask also, is MMM just a particular case of AAA with logarithms, or is it much more complicated than that? And
so you can combine. Because you can combine, so some models are equivalent, but in this case, not exactly. So there are some. ETS MMM is almost like ETS AAA for logarithms. You are almost right. It's up to Taylor expansion, first order Taylor expansion of ETS MMM. No, first order expansion of ETS AAA for logarithm will give me ETS MMM. They are not quite exactly similar. So basically, yes, basically you are right. It's a first order Taylor expansion, but the advantage of multiplicative and additive components, then you can combine. So for example, if you see something like, so the trend is roughly constant, but amplitude of fluctuations is growing. So you see something like this. Obviously, you do not see trend, so you see something like that. So in this case, what do I see? I see the trend is roughly the same. Yeah, the trend is roughly the same. It's not exponent. It's not exponent. But I see that when the indicator is small, the seasonal effect is small. When the indicator is big, the seasonal effect is big. So I conclude that it's multiplied by some. The increase is roughly constant in percentage terms, not in absolute value. So for these, I would prefer ETS AAM or probably ETS MAM model. Okay.
understood.
So in this case, because percent change, it's when something is multiplied by 1.1, it's 10% increase. So I would guess that in this case, I have a mixed additive trend, but multiplicative seasonality, and that you cannot cover by just taking logarithms, because when you take logarithms, all AAA is roughly transformed to MMM. Yeah.
Yes.
Okay, that's all for today. See ya next time. So next time we will go back into R.
Thank you.
Thanks for the lecture.
Thank you.
Bye-bye.
Bye.